There are some situations where we do not have an obvious symmetry to enable us to give a theoretical probability. Classic example is drawing pins. We've got some drawing pins here, and we can see some of them have landed pin down, and some of them have landed what we call pin up. When tossed, a drawing pin may land in one of those two positions, pin up or pin down. The probability of each outcome is difficult to predict, probably not equally likely, and may differ from one make of drawing pins to another. The weight distribution might be different in different drawing pins. Indeed it is. If you go and just randomly pick some off of a board or go to Officeworks and look at some different drawing pins, you'll see the weight distribution is different. So one way to deal with this is to toss a lot of drawing pins and see how many land each way. We then use what's known as the relative frequency to estimate the probability, and we'll look at that in the example that follows here. So we've got a set of 10 drawing pins, and we're going to toss them 100 times. So in total, that's the same as tossing 1,000 pins, 10 pins 100 times. 573 times the pins land pin up. What's your best estimate of the probability that drawing pins land pin up? So the probability of pin up is going to be the number of times that happened divided by the number of times we threw the drawing pins. So 573 over 1,000, or 0.573 if we give that as a decimal. Now, if we tossed it another 1,000 times, we probably wouldn't get the same result. So the probabilities would change each time we perform the experiment. But in all cases when you do this type of thing, the accuracy of the estimated probability increases with the number of trials. So we've got this for 1,000 trials, but we could be much more confident about the value if we did 1,000,000 trials.